Hello. I would like to demonstrate how to organize your code, and even more so how to think about organizing your code on a simple physics-motivated example. Here we're going to take a look at a simulation of a movement of a single planet, and we're going to try and apply the general reasoning of how to organize the code to this specific example. But before we begin, let's take a look at what the code does. We start, of course, with a couple of imports. That's all fine. So now let's go through the code line by line to see that we understand. Our goal is to simulate the trajectory of a particle as a function of time. We're going to do it by taking discrete time steps. The time steps are going to be small. We're going to take 1,000 time steps. Each time step has a duration dt, which is 0.1 in some units. We are simulating the gravitational potential, so according to the Newton's law of gravity. So this is the gravitational constant times the product of the masses of the particles, and we take it as 1. This is the array to store our coordinate, the array to store the velocity of the particle, the initial positions of both particles, the initial coordinate and the initial velocity. Here we take them perpendicular to each other so that the particle nicely follows a circular trajectory. And now we come to the simulation itself. We go over n steps. And with each time step, we first increment the particle's position by its velocity times the dt. It's a finite difference approximation to the corresponding differential equation. We compute the gravitational force as minus the gravitational constant times the coordinate of the particle divided by the length of by the distance between the particle and the origin to the third power. Finally, we increment the velocity by at each time step by force acting on a particle times dt. After we have done that, we have computed the complete trajectory, and we are going to plot it using matplotlib. Let's see whether the code works. So we see that our trajectory makes a spiral, and this is obviously not what happens in reality, but it also should not come as a surprise because we are using an approximation, and the difference and the reason why we don't reproduce a circular trajectory is exactly the lack of precision. There are more advanced algorithms that will solve this problem instead, but we are not going to touch that today. So let's think whether this code is good. And given what we see, we have to conclude that it is good. It runs. That's already great. That's the first thing we want to achieve. It produces a result. This result seems reasonable. And the code is super clear to understand. We went through it. It's short, it's nice, everything is good. So at this point, we cannot even, we don't have any complaints. The code is perfect. So let's try to use it. First of all, we said that the precision here is a problem, and if we had a higher precision, we would obtain a trajectory that looks more like a closed orbit. Let's try that. So to do that, let's copy this complete code. We would like to preserve this result, of course. So here's a new simulation. Now let's reduce the time step and increase the number of steps. Here by a factor of 100, that should be enough. Let's take a look at the result. Takes a bit longer, and we see that there is still some slight drift, but our trajectory still follows a nice closed orbit. There's plenty more. I probably added too many. Yeah, very nice closed orbit. It works. We have corrected the error. Now we here simulate a circular orbit, but we don't have to. Let's try to see what happens if we modify the parameters. So let's try to slightly increase the velocity. That nothing much changes. Now here we have an ellipse. And finally, if we take a velocity even higher, we obtain a hyperbolic motion of the trajectory, just the particle flies away from the origin. Can we ask the question again, is this code good? So observe that now our code has grown in size by a factor of 3, right? We copied the code twice. Now, if we wanted to fix an error or modify something, you would need to do it 3 times. And this also shows that the problem starts to creep in. If we want to run this code more than once, it's certainly not that great. It's hard to reuse. And this is a pattern that you should really consider when working. So if you find yourself doing a lot of routine work in order to achieve a result that shouldn't take this routine work, that is already a good starting point to think whether you perhaps should reorganize your code. Before you face this problem, it may well be perfect. So let's remove all the extra simulations and try to implement a function that does the same thing so that we can run more simulations easily. So, all right, the starting point is we are going to, of course, put everything into a function, plot trajectory. Now let's think a bit which arguments our function should take. It obviously depends on the initial position and velocity, so let's make it depend on r0 and v0. The time step seems to be like a thing which we want to change, and the number of steps. Let's now finish cleaning up the function. r0 is the initial position, v0 is the velocity. We provide dt and n as the input arguments. Almost done. As one last thing, we are now defining the strength of the gravitational force inside the function. Here, it's good to recognize that it's really a constant, and if we wanted to use it elsewhere, we wouldn't want to copy the same line again. So let's make it a real constant. And now we are going to assign this to GMM. Our simulation is ready. So let's now achieve the same results or try and apply this function. So let's try to first reproduce the initial simulation. So let's see, these are the coordinate and velocity, these are the other parameters. Let's try and see whether it still works. And indeed, it produces a very similar result. We can also we can also much easier modify the various parameters. So here we are going to increase the precision to obtain a more circular orbit, or increase the velocity and obtain a hyperbolic orbit. Very nice. Our code is much more compact now. And we do not need to change things in different places or copy a lot of code. All our changes are much smaller. This is great. Is our function good now? Can we ask about that? Can we still improve it? Now, once again, to answer this question, we need to think how we might want to use it. And we see that the function perfectly does what it should. It plots a trajectory given an input. But is plotting the trajectory really the only thing that we want to do? For example, we are nearly certain that we have implemented the code correctly. But what if we wanted to check? We see that the outputs are of the initial implementation and the new implementation look the same. But maybe there is a slight difference. Can we check this? Or for example, consider another situation. As you see, the precision of our simulation is an important parameter. So let's say we want to compare two simulations with different precisions. Will we make two plots? Well, plots are not really a convenient tool in comparing data. So if we wanted to compute an error, we would want to access the data. So this is another important observation. Our function should really return output in a convenient format. For that, let's reorganize the function so that it computes a trajectory instead of plotting it. So let's call a new function trajectory. Let's remove the plotting code. And we are going to return r, the coordinate. Observe that here we made a choice. We decided to not return the velocity even though we computed it. And if we, for example, wanted to check the conservation of energy, we would also want to compute to return the velocity as well. These are the choices that we need to make when designing functions. But for now, this is good. Another important reminder, observe that we changed the name of the function together with what it does. Now, this is important, and if you don't follow this principle, it will hurt you. Functions with confusing names will lead to errors in how you apply them. Do ensure that the function names and the parameters correspond to what they mean. All right, but our reorganization is done. So let's now try to apply the same function. So we don't have the plotting code anymore. Let's copy it. And now we can already plot the trajectory as we computed it. Works all the same way. However, having rewritten a function in this way, we can much easier compare the result. So let's take the previous code, the initial version. This is our reference, and we are not going to take it together with the plotting code, just the computation of the coordinate. All right, so now we have computed the array of all coordinates of the particle, and this function is a new implementation of the computation of the coordinates of the particle. So now, in order to check whether the new implementation is the same as old one, we just need to compare them. And indeed, we immediately see, with absolutely zero doubt, these implementations are identical bit by bit. This is perfect. Is our function working? Is our function well written now? Does it do what we want? It certainly returns a more convenient output now, so we can do more things with these functions. But let's consider yet another aspect. So remember, we discussed now the precision of our calculation several times. And whenever we want to change the precision, we needed to change two inputs to this function. First one was the time step, and the second one was the number of time steps, because we are typically interested in a certain total duration of the simulation, and not in a fixed number of time steps. So this is a final improvement we are going to implement. Namely, we are going to change from the number of time steps to the total duration of the simulation. This change is easy to implement. And after we have done that, we can simulate a function for a given number of simulate the trajectory for a given number of units of time or periods. So, for example, we can simulate it for 10 units of time without adjusting the time step, or we can adjust the time step, which makes the trajectory the calculation more precise, but does not change the rest of the parameters. We are nearly done. Now, as one final step that we need to consider, I would like to bring up the notebook environment. Now, this function that we implemented now is in a notebook. If we wanted to use it from a different notebook, we would either need to use some custom-made tools for importing functions across a notebook. However, a much more standard and reliable approach is to take the code that you do not expect to modify and put it into a Python script. Now, this code is almost perfect. We just need an extra import, because this function does rely on NumPy. And now we are going to write it into a file, which we are going to call Planetary Trajectory Py. We have written this file, and now we can run the simulation, the final version of our simulation, by first importing the simulation function, and running the simulation. Oh, just a moment. And everything works. So let's review what we have done and identify the most important principles. First of all, we realized that the structure of the code and the quality of the code is not an abstract concept that one can realize just by looking at it, but one always needs to consider how the code is used. We realized that good code is the one that needs a little modification in order for it to be reusable. Little modification means there is a lower chance of error and less work for whoever is using the code. We also realized that in order to organize the code well, we first of all need to introduce reusable bits. In our example, these are functions. And when designing these, we need to consider what their inputs are and what their outputs are. This is it. Now try to apply the same reasoning to any code that you're working on right now, and happy hacking!